I'm still trying to make sure that you understand every aspect of what? Elasticity. Welcome to Physics Meal. Today we are on elasticity part 6, and the topic we want to look at is energy stored in an elastic substance or elastic material. So let's begin. Now we know that energy is the ability to do work. Yes. When you treated work, energy and power, you heard that. The capacity of a body to do work. That's what we call what? Energy. So it means also when we talk about energy stored in elastic material, it means the ability of an elastic material to do work. Yes, that's what it means. It means the ability of an elastic material to do work. So energy stored in an elastic material is the ability of an elastic material to do work. So the question is this: can an elastic material do work? We have said that when we talk about energy, ability to do work. Now, energy stored in an elastic material is the ability of that elastic material to do work. So this is an elastic material. So the ability of this spring, which is an elastic material to do work, is what we call the energy stored in the elastic what? Material. Okay. Now, can an elastic material do work? Yes, an elastic material can do work. We are going to see examples on how an elastic material can do work. But before then, an elastic material can do work through compression of the elastic material or stretching of the what? Elastic material. So an elastic material can do work through the stretching or compression of the elastic what? Material. So an elastic material can do work either by stretching the elastic material or doing what? Or compressing the elastic material. So let's see the work. Let's begin with the stretching. You know catapult, right? If you place a stone in a catapult and you stretch it, if you release the stone, it can do certain work. For example, if you have a glass cup and you release the stone, if the stone hits the wall, the glass cup, it will break the glass cup. So the stone has done work by breaking the wall, the glass cup. And the energy that enabled the stone to do the work of breaking the glass cup came from the wall, from the elastic what? Material. It came from the elastic material. Okay? Now, for compression, if I have a spring, and I drop a load of mass on this spring, you know, it will compress it. So we have something like this now. The load will compress the spring. It will reduce the size of the spring. If I'm holding my hand here, the compression will continue to exist. But if I remove my hand, you will notice that this spring will lift this stone up. So the spring has done work of lifting the stone up. And the energy that lifted this stone is as a result of the energy stored in the what? In the spring. So you can now see that an elastic material can really do work. It can do work. Yes, it can. So it can do a lot of work. Even in tailoring, you know, the add rubber. Huh? Yeah, the add rubber on the skirt or trouser. So it's doing a certain work there. Don't mind me. So let's go back to physics. Now, this energy is known as, this particular energy, we have said that energy stored in an elastic material is the ability of the elastic material to do work. So we decided also to explain how elastic material can do work. we say that it is when you stretch the elastic material or you compress the elastic what? Material. The energy stored in an elastic material is known as the elastic potential energy, and it is equal to the work done by an elastic material. So this energy stored in an elastic material or elastic substance, we are going to call it elastic potential energy, and this energy is equal to the work done by an elastic substance or elastic material. So what now is the work done? The work done by an elastic material is equal to the product of the average force acting on the material and the extension or compression. So we can say that work done by an elastic material is equal to average force times extension or compression, either extension or compression. So if we use W as the work done, and we use F as force, and we use E to represent extension or what? Compression, we can now have that W is the average force, that is half times what? E. So W becomes 1/2 Fe. So I can call this equation 6. Our last equation was equation 5. So this becomes equation 6. Okay, now, so let's move further. In this place now, we know that we have defined F before as force. So let's define let's state the meaning of all the terms, even though we know F is force. So where W is work done by an elastic material, and F is the force in Newton, and then E is extension or compression. Okay, now we can actually modify this equation further. Yes, from Hooke's law, sorry that I'm mentioning Ohms. From Hooke's law. You remember Hooke's law? From Hooke's law, we have that F is equal to KE. That's from equation 1, right? If we substitute the value of F into this equation, equation 6. So substitute the value of F from 1, that's this equation 1, we derived it in the first video, or be in the second video, from 1 into what? Equation 6. To have that work done now is 1/2 K is KE to replace what? To replace F here. So you have KE. So KE times E will give us KE squared. Where K, of course, is the force constant or elastic constant. You remember that we explained elastic constants in that video. I think it should be either part 2 or part 3 of what? Of elasticity. So you search for the videos. Search for the videos. I will leave a link to the videos in the description. So you search for the videos so that you can watch it. Okay? So we have this. We cannot actually go further because from here, if we make E the subject of formula from equation 1, we can have another equation for work done, connecting what? Connecting force and the word force constant. We can have that. And if I want to achieve that, I can say from equation 1, so from equation 1 again, from equation 1, I can have that E is equal to what? F over K. Therefore, equation 6 can be modified to work done equals what? 1 over 2 F squared over what? K. Okay, let's write it separately. 1 over 2 times F squared over K. So I can call this, what was my last equation here? This is 7, equation 7. Then this is going to be equation what? Equation 8. Equation 8. That's what I'm going to have there. Equation 8. Okay? So, 3 different equations that can help us to calculate energy stored in an elastic material, which is equal to the work done by an elastic material. We have said that the work done by any elastic material is equal to the energy stored in the elastic material, and that energy we call it the elastic potential energy. Okay, now we are not done yet, just few things more and then we'll be done. Okay, now using energy conversion, this elastic potential energy can be converted to kinetic energy. Yes, it can be converted to kinetic energy because if, for example, you release a stone from what? From a catapult, the stone will be in motion. That means from a potential energy, from being at rest to being in motion. So the potential energy has been converted to what? To kinetic energy. So when that happens in energy conversion, you will still see that the elastic potential energy stored will still be equal to the kinetic energy. Yes, it will be equal to the kinetic energy. So let's make a statement. So let's note this. Note. If the elastic potential energy is converted to kinetic energy, then the elastic potential energy will be equal to the kinetic kinetic energy. Will be equal to the kinetic energy. So what is our elastic potential energy? Is half F E. And what is kinetic energy? 1 over 2 mv squared. So I can call this equation 9. Equation 9. That's it. I can call it equation 9. Remember that this elastic potential energy is still the same thing as this. So in place of half Fe, I can still replace what? Replace half Fe by what? Half Ke squared. I can still replace this, which is the elastic potential energy or the work done by an elastic material. I can still use this equation to replace it. So I don't want to be repeating so that we'll have multiple equations. So just note that since this is equal to this, because they are all work done by an elastic material, it's still possible and it's still true that this is equal to this. and this one can be equated to this, and that is when an elastic potential energy has been converted to what? To a kinetic what? Energy. So that's the first point to note. And similarly, if the potential energy, if the kinetic energy results to a potential energy, or if an elastic potential energy results to the body moving through a certain height, it also means that the elastic potential energy can also be related to the potential energy of another body. Let's take for example, if the compression of a spring results to a body moving upwards. So when a body is moving upwards, it's covering a height, right? That means the height covered is what determines the potential energy. So we can still relate the elastic potential energy with what? With potential energy. Another thing that we can note is this. Supposing a body of certain height, a body of certain mass rather, is placed above a spring, right? And maybe through a certain height, right? If this body should fall through this height, it has a potential energy. So already the body at this height has a potential energy which is based on this height. Remember that potential energy is mgh. So if this body falls through from here, it has expended its potential energy, and it is this potential energy that will compress this spring, right? So that potential energy that will compress the spring is also equal to the energy stored in that spring. And in such a case, we can actually say that the energy stored in a spring, which is half Fe, is equal to what? Mgh. And that will give us maybe equation 10 in a case like this. Do you see that now? In a case like this, we can have an equation like this to solve, that's to use and solve a problem like this, because here this body has potential energy, and it is this potential energy of this body that will compress the spring, right? And the energy required to compress the spring now is the energy stored in the spring, which is elastic potential energy. That means this elastic potential energy is equal to the potential energy of this body. So we have about 10 equations that we can actually use so far. Remember, we generated 5 previously, and now we also obtain another 5. We have not finished with the equation, but don't be afraid. They are equations that you can easily remember. All right. In our next class, we are going to see that energy stored in an elastic material can also be determined graphically. Yes, we can actually determine the energy stored in an elastic material graphically. Don't miss that particular class. Yeah, it's going to be very delicious and interesting. See you in that class.